Okay, so let's start with the topic of radioactivity, which is for the MCAT, the problems are quite simple. So even this one, which looks challenging because they tell you a whole story, it's actually very simple. And because you don't need a calculator, the math is going to be very simple as well. So they talk about a smoke detector and radioactive decay of Americium-241. Okay, so you might want to stop the video and try to do that on your own, but it's actually really easy. Okay, so before doing the math, I just want to tell you the story behind that. It's interesting. So if you go over my videos, you know that you have three types of radioactive decay. Okay, you have alpha decay, beta decay, and gamma decay. So alpha decay, that is what the problem is about. So in that case, it's a helium nucleus that is being emitted. Okay. So it's not that dangerous for you because it's going to be stopped by dead skin. So alpha decay, helium nucleus is emitted, right? So let's look here at my slide. You see alpha decay. So for example, you start with uranium-238 and it's going to decay into thorium 234. And you see that two protons have left. And here you have two neutrons. Okay. So you lose two neutrons and two protons. So it means you go from 92 to 90. So that means the mass number is going to decrease by 4. And that will be the nucleus of helium. And you see that the equation is balanced because 90 plus 2 is 92, 234 plus 4 is 238. Okay, so two protons have left and two neutrons have left. Okay, so that means the atomic number has decreased by 2 and the mass number has decreased by 4. And the helium, the nucleus helium, will combine with electron and it will become a helium gas. And that's how we get helium gas, right? We harvest it from inside the earth. You cannot make it. It's a noble gas. And you use that for the balloons, for example. So here, just as a practice, you can try to do this one, right? You have plutonium 94. So it's one of the isotopes of plutonium. What is this nucleus here? Okay. So you can stop the video and try to do that. So I'm trying to do like a short review, right? So here you can call that X. You see, this is 2 here, and this is 94. So that has to be 92. This is 4, and this is 242. So that has to be 238. And if you have your periodic table, a number of proton equals to 92. That means that's going to be uranium. Okay, it's going to be uranium-238. Okay, so uranium-238 has all uranium, any isotope of uranium will have 92 protons. So uranium-238 is the most common isotope of uranium when you take a piece of uranium from the ground. And it will be 99% of the naturally occurring uranium. Now you have uranium-235, which is about less than 1%, right? And that's what you need if you want to make in nuclear power plant. You need to enrich uranium-238 to get uranium-235. If someone wants to make an atomic bomb, which is not a good idea, you still need to enrich uranium to get enough uranium-235. Otherwise, you also have another type, another isotope, but it's very little. You have uranium 235, and you have like 0.0055%. Okay, so that's just a tangent that I'm taking. So a nice application, and that's what the MCAT is talking about. Nice application will be a smoke detector. Okay, so you have two electrodes here. So this one is negative, this one is positive. Okay, and it's a review also of electricity, right? So it's connected to a battery. So here you have a 9-volt battery. So this is inside your smoke detector. You see, this is the americium, which is an alpha emitter. And here you place your piece of americium, and the alpha detector, it's gonna ionize the air in between the electrode, so electricity can flow. So electricity will be able to flow and nothing happens. Now, if you have a fire, you can have smoke. Okay, so smoke. So then the alpha particle, which is positive. Okay, alpha particle are positive, right? Because it's a nuclei of helium, so it's missing two electrons, now are going to combine with the smoke particles and no electricity can flow. Okay, so then an alarm can be set. I think that's what the problem says, right? Let's see, right? Ionized air molecule move toward the oppositely charged plate, so it's being ionized by the alpha particles, right? Because the alpha particles need electrons, so they're going to take it from the air molecules, right? Because the nuclei is positively charged, so it's missing two electrons. So it's going to take the electrons from the air molecules, and you have a small current. If you have smoke, then those ions will interact with the smoke, okay? And then the current will decrease and will trigger the alarm. So that's what the problem is talking about. So that's about smoke detector. So they try to confuse you with the whole story, but actually the problem is very simple. Okay, so what is the problem? Ask. So they say, how long does it take? So it's radioactive decay. Okay, how long does it take to go from 80 million nuclei to 5 million nuclei? Knowing that every 432 years, it's going to be divided, the number of nuclei will be divided by 2. So you don't even need to know the equation with the exponential. You know it's an exponential decay. So here you have the number of nuclei, let's say in millions here, and here you have the time, and I'm going to put the time in half-life. So the half-life is 432 years. So it means after 432 years, half of the nuclei will be divided by 2. Oh, I mean, the nuclei will be divided by 2. Okay, so it takes 432 years for half of the nuclei to decay into helium and the daughter. Okay, so it goes from here. Let's say you have 80 to begin with, and you see that after one half-life, you're going to have 40. So you're going to be here. After two half-life, you're going to have 20. Okay, so it's going to be here. I'm going to make a cross here. And then another half-life. Okay, so three half-life, it's going to be 10. So it's going to be here. And after 4 half-life, you're going to have 5. Okay, so this is called radioactive decay. So each time it's going to be divided by 2, divided by 2. So it's an exponential decay. Okay. So to get to 5, so this is 5, it takes 4 half-life. So 4 times 4, 32 years. It's going to be, if you do the computation, you can do it with in your head. You don't need a calculator. It's going to be 1728 years. Okay, so that's the first way to do it. Okay. Second way to do it, you can say, okay, you start with initial number of nuclei n sub 0. Okay, and you're going to divide by 2, and you're going to divide by 2, and you're going to divide by 2 every half-life, and at the end, you're going to get that number here. So that number here is 5 million, which is 80 millions times how many times it has been divided by 2. Cross this. So you're going to have 5 over 80 equals 1 over 10. You can simplify it. So you have 2 to the n is going to be 16. So n equals 4. Okay, so you have 4 half-life. So the time will be 4 times 4, 32 years. And then if you really want to do the hard way, why not? Then you can write the equation, which is the equation for exponential decay. Okay, so here you have lambda, which is natural log of 2 divided by the half-life, and you can solve for t here, right? So here you're gonna have 5 equals 80. Okay, so you're gonna have 1 over 16 is E. Okay, so you have to take the natural log on both sides. And at that point, you need a calculator. And if you solve that, you're still gonna get the same thing. But why do you want to do it the hard way when you can do it the easy way? So that number 1 and number 2, it's much easier. Okay, so again, this is Americium. It was discovered in America, obviously. Right? Okay, so that question is very simple. Again, it's an alpha decay. They might ask you what's going to be the daughter, right? So we start with americium, and then americium is 241. The number of proton is 95. Okay, it's going to give you a americium helium nucleus, which is 2 protons and 2 neutrons and 2 protons. So here you have 4. Can you find this nucleus here? That could be also a question. So to get to 95, you need a 93. To get to 241, you need a 237. That's here. And you don't need to know that unless you can use the periodic table. This is called Neptunium, okay, which is also radioactive, very unstable. So it's going to be called Neptunium 237. So americium was discovered during the Manhattan Project by the scientist, I think his name was Seaborg, right? And then Neptunium, I'm not sure, but it's named after the planet Neptune, which is not a planet anymore, and it just follow uranium. So uranium, Uranus, Neptunium, Neptune. Americium follow the element europium, which was named after Europe. So that's for the little story, but that could be also a question here, which is quite simple. So let's look at the next question, and it could be a tangent here. They are asking you the magnetic electric field between the two plates. Okay, so this is very simple also. If you remember the electric field between two electrodes, right? It's very much like the two parallel plates capacitors. So you have one electrode here, which is positive here. Here it's going to be negative. So you're going to have an electric field in between, and the voltage applied here. Okay, so let's forget about, so here you have a battery. So let's say this is 6 volt, and the distance here, that distance here is, I forgot, I think it's 2.5 centimeters, which is 0.025 meters. Okay, so the electric field, remember, the equation is volt per meter. So the equation here, when you have a uniform electric field, which you will always have, okay, it's going to be the voltage drop over the distance here, so delta x. So it's like a slope. So the electric field will be 6 divided by 0.025, and it's about 240 volt per meters. Okay, I think that's it.